Thank you for the intro. So I come here to talk to you about the trust, right? Trust is essentially everywhere in modern economies, also ancient one. So one example is, for example, currency, right? Money, or in the words of the general manager of the bank for international settlements, money is established, right? It's built on the trust the public puts in it. And when people don't trust the currency, the central bank running the currency, or the people working in the central bank, what we get is hyperinflation, right? My favorite hyperinflation case is Zimbabwe. They had to print $100 trillion bills because the value depreciated so fast. This is what you get when people don't trust the people running the currency. That's why it may seem blasphemous to imagine a currency which is not established on this traditional form of trust, right? Trust being the central bank. But that's exactly what Satoshi Nakamoto, Bitcoin's creator, sought out to do. Bitcoin, in Satoshi's words, is an electronic currency, a digital currency, which tries to replace this old notion of trust with something new, cryptographic proof, a cryptographic notion of trust. So let's try to understand what that means by comparing Bitcoin with a different electronic payment system, PayPal. PayPal is centralized, right? It's operated by one company, PayPal. It's permissioned, meaning that if you want to use PayPal, you have to sign up and ask for permission, right? They have to let you in. And when you sign up, you have to tie your digital identity to some real world identity. For example, by presenting some government ID. In addition, traditional platforms like PayPal are sometimes prone to monopolization. If a company, a platform, is indeed a monopoly, they can extract higher rents from consumers. They can charge more than they would in a competitive market. And in the words of Peter Thiel, PayPal's co-founder, right? Competition is for losers, right? So you're laughing, but like, whose side are you on, right?
Not on his side.
Not on his side. I'm on his side because this is like great material for a job number. So he said, if you don't want to be a loser, if you want to make money, then the way to do that is building a monopoly, right? They're not even afraid. They're not even shy about that. So how do things change in Bitcoin or in blockchains in general? Bitcoin is one example of general class of mechanisms that I'm going to refer to as blockchains. Bitcoin is decentralized. It can have more than one operator. It's permitted, but if you want to join the system, whether as a user or as an operator, you don't have to ask for permission. And it's pseudonymous, meaning that when you join, you don't have to tie yourself to some real world identity. You can create a fake name if you want. These properties combined solve the challenge we just saw. This is shown, for example, in a very, very nice paper that I really like by Guru Huberman, Jacob Leshno, and Siamek Mulemi from Rista, published in 21. They show these properties solve that issue. This is also demonstrated empirically when taking a look at modern blockchains that allow transferring assets, for example, assets that are equivalent to the US dollar. Transferring these assets can be much cheaper than when using traditional systems. But it seems that while we may have solved one challenge, we perhaps introduced a new one, right? Let's say a criminal wants to join our system. We can't say no because we're... Go ahead.
You say that's the cost, you take into account the cost of energy?
This is by McKinsey, right? Whatever they say is right here.
Responsible for your
So this is for proof of stake blockchains. Energy costs are negligible, right? You literally run a server exactly like traditional platforms. So it seems like we perhaps introduced a new challenge, right? A criminal, let's say, can join our system, and we can't say no because we're permissionless. The criminal, we wouldn't even know that he or she are a criminal because the system is pseudonymous. They don't have to say, I'm Kim Jong-un, I'm whatever, right? They don't have to do that. So the criminal can join, do bad stuff, run away, and perhaps we wouldn't be able to trace them and hold them accountable for whatever they did. And this is where this cryptographic notion of trust comes into play. Instead of having to trust the system's operators, maybe bad people, we should trust the mechanism. If the mechanism makes sure that performing attacks is either impossible or just unprofitable, then we're good. And the way to go about doing that is to understand the threats we are up against. Once we have that understanding, we can design systems which are robust to these threats, and evaluate different designs, less you, that are robust to the threats that we should expect. So luckily for us, many smart people have thought up of all kinds of threats, right? But these were not observed in practice. One example is the threat model by Yaish and Mingun. They come up with an attack which they show to be profitable on Bitcoin as it was in 2013, was published a year later. It was profitable back then, it's profitable as of today, not just on Bitcoin, but on many other blockchains. And this is a bit peculiar. There is a method to making money, right? And people are not using the method to make money. If people like making money, people are not making this money. What gives? Okay. It's not just for that attack, it's also for the others. As far as we know, we don't have empirical proof that these threats are being materialized in practice. In this talk, I'll present you, among other things, my threat model, which was observed. I observed it. And so will you in a bit. So to give you some background, or maybe an overview, I came up with an attack which I'll present to you. I show that it's profitable and that it's practical. I can pull it off on deployed systems, locally deployed systems. And given that I could pull it off, I thought, well, maybe someone did it in practice. So I scraped Ethereum, the second largest blockchain after Bitcoin. And I saw that someone was performing a weaker variant of my attack. Okay. The second largest actor at the time was performing a weaker variant of my attack. After I went public, they weren't shy about it, like Peter Thiel. They were proud. Can't stop appreciating this elegant implementation of what we've done. And this elegant implementation is you. Okay. Again, on the good side, right? Tell me. Okay. So if this is elegant, then expect nicer things. And this goes to show several things. First of all, if there's money to be made, people will make it. Okay. It's not that it's some property of nature that people won't attack blockchains because the previous threats were not observed. It doesn't mean that they're not valid threats, but perhaps something in practice prevents people from pulling them off. Coming up with proper threat models is quite delicate. It's the fine art. So given that the threat is real, we better understand how to design secure systems. And towards that end, I employ all kinds of tools. In this talk, I'll focus mostly on the attack, which I just briefly mentioned, and on another more econ flavor type of work. So by a raise of hands, how many people here know about blockchain? Oh, nice. Okay, wasn't expecting that. Cool. So to those of you who don't know, blockchains are digital payment systems. Right? They let people move money around, transact. So if our users want to transact, they create transactions and send them to the operators of our system. The operators in Bitcoin are called miners, so I'm going to stick to that. They may be called different names in other systems. Let's just use miners. Miners process transactions by collecting them into batches called blocks. for a block to be valid, it should contain two things. First is a pointer to some previous valid block. This is why we have a blockchain. And second, a solution to some hard puzzle, a hard challenge. And the mental model you can have for that is that essentially all miners participate in a competition. All of them want to be the first ones to solve the challenge, to create a valid block. Okay. Once a solution is found, we have a valid block, we can publish it to the world to see. Because creating a block is hard, the puzzle that needs to be solved requires some work. We give a block reward to the miner who created the block. We mint money, we print money and give it to that person or set of people. In addition, the miner who created the block can also collect the fees paid by the transactions in the block. One very reasonable thing to want from these protocols is that they be fair, meaning that if someone did some fraction of the work, then that someone would receive an equivalent fraction of rewards. Given that the block creation process is probabilistic, this puzzle is kind of like participating in a lottery. Anyone has some probability of winning. It may be the case that two people create two valid blocks roughly the same time. This is bad. This is bad because these blocks may contain conflicting transactions. Let's say all of my property, everything I have in the world is 1 Bitcoin. Okay. The yellow block may contain a transaction where I give all my money to Zal. Right? The green block may have a transaction where I give all of my money to Yaish. Picture close. Obviously, they cannot coexist, right? We don't want that. So the way to get around this is the longest chain, or the most difficult to create chain. Each block requires some amount of work to create. We sum up all the work represented by the chain, which culminates in each block, and we compare the magnitudes of work. We go for the chain which represents more work. If all conflicting chains, some of them, represent the same amount of work, we employ a local tie-breaking. For example, we go for the first block we've seen. If we have a reasonable local tie-breaking rule, then with overwhelming probability, eventually ties will be broken. So someone would create a block which extends one of the chains, and with some probability, no one else would create another block. Just need to wait sufficiently enough time. In Ethereum, when I wrote this paper, blocks on the longest chain were called main chain blocks, and those not on the longest chain were called uncle blocks. Uncle blocks are not able to collect any transaction fees and can only collect a partial amount of the block reward, not the full amount. The last thing we need before we can dive into the attack is the difficulty adjustment algorithm. It may seem reasonable to think that if many miners join our system, then blocks will be created at a faster rate. Right? More miners, more blocks. We don't want that, right, intuitively, because that would lead to more disagreements, which we don't like. And vice versa. It may seem reasonable to think that having fewer miners means that blocks will be produced at a slower rate. And we're a payment system, right? We want to process transactions at a sufficiently fast rate. So this is also not ideal. You can think of the block rate as having kind of a Goldilocks zone. The way to maintain the block rate within this Goldilocks zone is the difficulty adjustment algorithm. It measures the average time between blocks. If it's too high, the puzzle that needs to be solved is too difficult, so we lower the difficulty, and vice versa. To be able to objectively measure time, objectively measure the block rate, irrespective of a miner's location in the network, we timestamp blocks. When a miner sets out to create a block, miner shoves a timestamp into the block. This, among other things, determines the puzzle that needs to be solved, meaning that after solving the puzzle, we cannot go and retroactively change time. This would invalidate the solution. And this is what we're going to break.
אביב,
Go
אתה
ahead.
יכול רק לתת דוגמה למה זה הפאזלים האלה שאתה מדבר עליהם?
So you need to, the puzzle defines a number, okay? You need to find an input to a hash function such that the output would be higher or lower than whatever you want from that number, okay? This requires work, right? You have to go through, you have to churn, otherwise the hash function is not secure.
The rate is only regulated according to the supply of how many miners there are. The demand, how many transactions you want, is not relevant.
In these designs, the demand is not relevant. Okay, and it's not how many miners there are, it's how much compute they have. Right? Yeah, but that could be an interesting design, like what you propose. And the interesting part about it is how can you make sure the rate is not too high, right? If the demand is high. Yeah, go ahead.
How do you control the rate if there's nothing centralized?
If there's nothing what?
Nothing centralized. How do you decide on the quiz and how do you control the rate if there's no central authority?
So God gave us the rules of the game, right? That we follow. Right? Everyone who wants in on this game should follow this difficulty adjustment algorithm. If you disobey the rules and the majority follows the rules, then you're out, right? You're playing with yeah.
Okay. So there is God here in the system.
I mean, the creator of this.
Okay.
People can come together and decide on changes, but they'd have to arrange a majority, right?
But if the puzzle is updated automatically or by
It's updated automatically, but the algorithm is determined by the designers.
Well, that's okay.
Is the quiz itself known publicly?
Yeah, it's so the general format is what I've just said to Oded, right? The difficulty determines the magnitude of the number, right? If the number is lower, you require more attempts before you find a suitable pre-image, suitable input. The very, very super specific puzzle that a miner needs to solve is, among other things, well, not among other, it's a function of the block. You assemble transactions, you shove a timestamp, the block also contains all kinds of metadata. This gives you the puzzle. You shove it into a function, you do it something. Okay?
So operating at a different rate would not be in my incentives as a miner? I mean, what prevents me from kind of disobeying the rate?
So if you disobey, I mean, when you say disobey the rate, what does it even mean, right? Like the block creation process is probabilistic. It happens that sometimes two blocks are created one after the other. Right? Sometimes.
I mean, there is some algorithm I need to run, right?
Yeah.
This, rate algorithm that you mentioned.
Yeah.
It's something that I run as a miner.
So
I can change that algorithm. I mean, why shouldn't I?
if you change it, and if you change it such that the difficulty should be lower, then if the majority don't follow your new algorithm, then they would see your block and say, well, this is invalid. We ignore that. Right? If it's more difficult, then you're golden, but like, why would you want to do that? Unless you are going to do something else. Let's see. Okay. So
To piggyback on this question, how
Is
do
it-
the system know how much compute there is?
then this is exactly the difficulty adjustment algorithm. You look at the average rate, right? If it's too high, right? It's beautiful. Really. So now let's talk about the attack. Let's say that this is the latest block. Okay. if we were following the longest chain rule, we should have been trying to create this block. We're going to not do that. We're going to create a conflicting block. Red, bad, green, good. Why would we want to do that? Maybe B1 has a very lucrative transaction, right? Very rare in the magnitude of fees it pays. Very rare. We can expect to see such high fees once every million years. So wouldn't it be nice if we could collect these fees and not that other person we don't know and don't care about? This is, among other things, what you get by doing the attack. You also get other things as well. The first major result in the paper shows that sometimes you can create a bad block such that it's more difficult than the block we're trying to replace, meaning that we're displacing that block. That block becomes an uncle, we become the main chain. And while it is harder, more difficult than that block, it's not more difficult than the block we should have been trying to create. Okay? And this is part of the magic. Okay? Intuitively, you take, if you use difficulty adjustment algorithm, we take the difficulty relation I've just described and use it to create a set of equations, we solve them. Okay? We show constructively if you have these and that conditions, you can pull off the attack. And to pull off the attack, you should set your timestamp to be this and that. Go ahead.
But at the same time, others are trying to extend V1. So
Exactly. The point is that you would have been trying to extend V1, right? You can do this, right? Nothing changes with respect to, let's say, because this is not more difficult to create than this, from your perspective, this cannot be worse, at least myopically, right? It's not more difficult, how can it be worse? If it replaces this, you are still on the main chain, right? Just as if you were trying to do this, right? So this shows a couple of nice things about the attack. First of all, manipulating timestamps, not common. Most other attacks relied on hiding blocks, block withholding. You create a block, you hide it, then you publish it sometime in the future. To pull off such attacks, you should have really good internet connectivity, right? You're hiding your block, and you should publish them before someone else succeeds in creating a block. To do that, you need to be very fast.
How can you prepare in advance if you don't know the last block?
For the block withholding attack,
You need to record the previous block in your block. So how do you prepare? Can you prepare much in advance?
no. So the point is, you created a block which extends the main chain. Okay? It's a bit orthogonal, but like briefly, you create a block which extends the longest chain. You don't share it with the world, you hide it. Someone else will also create a block. If you have very good internet connectivity, you can rush and
No, that was not my question, but I don't want to disturb further. But my question, I'll ask my question, you decide if you answer.
okay.
You said that in the new block, I have to point, I only have to point, or I have to contain some data from the old block.
You have to include the hash of the old block.
So you can already prepare all this in advance, even though other blocks may get in,
For the other attack,
or either.
so for all attacks, you have to include the hash. The point, in my attack, everything is observable, right? Like this is observable. You don't hide your block, right? I'm trying to show the difference. You don't hide your block.
Okay.
For the other attack, it's a different story.
Okay.
We'll talk about that.
Can you please explain again about time steps? Timestamps. You need the timestamp of BA to be earlier than
B1.
B1? Okay.
But it's a fine art. Like just shoving any earlier number may not get you what you want. Like it would be more difficult, but not necessarily at most as difficult as that.
Okay.
Follow up on Amos' question. So you're trying to extend B0 by BA, and many people are trying to extend B1. Yeah, so since you're a single agent and there are multiple agents trying to extend it, so they have a much higher chance to do it before you.
The point is, from your perspective, right, let's do the right thing. You're trying to extend this. Each person is trying to create a BH of its own. It's not a shared BH, right? You have a BH of your own. Other people have exactly the same chance of creating their own BH, irrespective if you try to create your BH or your BA. Other people are fixed. And what this shows is that when trying to create your BA, you're not incurring more work than if you were trying to create your BH. Your perspective, this myopically is not worse.
Yeah, I agree, but you have a low chance to.
But the chance is the same either way. The second major result, we show that the attack breaks fairness. We can increase our share of profits. Okay? When we increase our share of profits, we decrease others, which is bad. Okay? To do that, we model the mining process as a markup process. We solve it, and a nice thing about our proof is that we show that in each of these transitions, you cannot lose when compared to doing the right thing. You can only, sometimes you earn exactly the same as if you were doing the right thing. Sometimes you earn strictly more, you can never lose. Okay. So taken together, right? And we also show that when considering fees, you can increase your absolute profits, not just your share, but also your absolute profits. When taken together, you increase both your absolute and relative share. Go ahead.
So one could imagine Bitcoin has no timestamps at all, no timestamps in the block. So you just follow the longest chain. Then would your attack still be relevant? I mean, I'm trying to.
So if you only have timestamps, then
you have no timestamps.
If you have no timestamps or like fixed, let's say, that the attack won't work, but then how would you be able to be permissionless and not have a too high block rate? Right?
Well, the difficulty adjustment just looks at the overall block. It doesn't have to look at timestamps, right? It just has to look at how many blocks have been produced over a period of time.
You said a period of time.
2 weeks. I mean, I think so.
How can you measure 2 weeks?
Okay, good question.
Right. We can talk about it later. You're not on my schedule, but I'm not angry. So this is the offensive side of things. I also try to solve things sometimes. I present some mitigations, but the point is we are attacking the difficulty adjustment algorithm, which is really a very important part of these types of blockchains. Okay. In the paper, we present some intuition as to how this can be performed on other blockchains. And in a very, very nice recent work by CC1 from Tsinghua University, she has shown that variants of this attack are applicable to Bitcoin and to any other blockchain similar to Bitcoin, Nakamoto style incentives. I also have other attacks, if you like attacks. And if you do like them, then I encourage you to read the papers and come talk to me after.
The difficulty rate adjustment is due to past rate or current rate?
In Ethereum, the rate is based on the current time since the last valid block. In Ethereum, as it was when I wrote the paper. In Bitcoin,
So say in Ethereum, wouldn't you always want to manipulate your time step to be as close as possible so that you will get a weaker puzzle?
So as close would give you a more difficult puzzle.
A more difficult.
But that would, like, if you don't do this carefully, right? Like, if you don't do this carefully, then you're incurring a lot of extra work, which is not always worth it. The magic of the attack is I show exactly where you hit the sweet spot. Like, you're more difficult than what you want to replace, not more difficult than the good thing, right? So you cannot be worse off, right? Doing that, you may be worse off.
Okay.
Okay.
So what was this backdoor fixed or?
It's not a backdoor, it's a problem with the protocol.
Yeah.
And 2 months after they,
Got the wrong.
no, don't worry, don't worry.
All the security people.
They completely changed their protocol. Okay, 2 months after they moved to proof of stake. Doesn't require any form of work and thus doesn't require timestamps, at least not in the form that was required before. Good. So let's.
That was because of that.
So saying because like a causal effect is difficult to tease out there.
There are many problems with the protocol, or
Out of respect, I won't say that. This is going to be on YouTube. I like them. I like the Ethereum Foundation. So they have been wanting to change their protocol for a long time and kept on pushing it forward. I don't know whether this caused them to change or not. Cool. So let's talk about options, a more econ flavor. As we said, we don't like disagreements, right? One way to get disagreements is if our blocks were big. Bigger blocks, slower to propagate, more disagreements. One way to solve that, right, that challenge is just to place a hard cap on the block size. Let's say block can contain at most 2 transactions. The problem with this fix is that sometimes the demand for block space, right, the amount of transactions vying to get into a block may be greater than the block cap. In Ethereum, when I took this picture, there were 40 times more transactions than the block cap. 40 is a large number. So we have scarce resource block space. And what do we do with the scarce resource? Increase the cost. That's one thing. You like making money, I can tell. Right? We better give the scarce resource to the people who really, really want it, right? This is the economically efficient outcome. How do we do that in Bitcoin? As we said, users can attach fees to their transactions. Let's say we have 3 transactions paying 90, 40, and 1. If the block size, the block limit is 2 transactions, and if our miner likes to make money, right, then the miner would choose the highest paid transactions. The fees are a costly signal as to the value users place on being included in the block, right? The miner's profit maximizing strategy would result in the efficient outcome. The problem with this is that this design may make it hard for users to know how to set their fees. These 2 transactions could have paid 1 plus epsilon and still would have gotten in, because that's more than 1. But to figure out that they could do that, they would have to collect historical transactions, devise some probabilistic model for the transaction arrival rate and the distribution of fees, and given that, figure out, oh, my value for getting in is this, but according to the model, if I set my fee to be that, then I would get into the block with some probability, and so on and so forth. That's not easy. We don't want to
use public knowledge.
Public knowledge. That's not easy. We don't want our users to bother with that. We want them to have a nice ride, a nice experience. In our terminology, we want the mechanism to be user incentive compatible, UIC. What does that very exactly mean? Imagine a world where users declare their value for getting in, and the mechanism does the hard part for them. If the mechanism says, oh, this is your value, the minimum amount you can pay and get in is that, so that's what I'm going to charge. That's exactly what we want. In this case, that would be 1, right? Those people will pay 1 and get it. If you noticed, I hope people noticed here, that this is essentially a first price option. I say I hope because I know some people here do options. If you haven't noticed that, that's fine. It's fine. Okay, this is a first price option. In this analogy, users are bidders. The item they're bidding for is slot in the block. Miners are our auctioneers. And given that this is an auction, well, the people designing blockchains have thought to themselves, we better have the nicest auction format for our blockchain. Vitalik, for example, Ethereum's co-creator, thought that as well. Talked to very smart people like David Easley, Scott Buchananers, and even went to EC, where people who know their auctions go and meet to figure out how to design the best auction format for Ethereum. But given that auctions have been studied for a very long time, and that we know of all kinds of very nice auction formats, why not just take some off-the-shelf design and be done with it? People have won Nobel Prizes for their auction work. It can't be that we don't have a suitable format. So the problem is that the traditional auction framework is perhaps not an ideal fit for the blockchain setting. Let's see why. So let's take a look at the third price auction. In our running example, the third price is 1. The third price, given that we sell 2 items, given that our block can contain 2 transactions, the third price is the highest fee among all transactions not included in a block. The third price is 1 here, which is exactly what we wanted to be user incentive compatible. The problem with this mechanism is that the miner can create a fake transaction, a shield bid, to jack up the price. For example, transaction paying 41. Now the third price is 40. The miner gets 40 from this transaction. This transaction is taking money from one pocket, putting it in another. The miner increased revenue by a factor of 20. Very nice. You can even pull off a nicer attack if you really want. So if you can think of that, come talk to me after and we'll exchange our. Okay. But I promise you a better attack.
39?
What's that?
Why not 39?
So 39 would give you extra profit from this, but if someone else picks up on that transaction, and someone else would, because the transaction would flow around, right? It won't be in your block. Someone else could pick it up, then you'll pay 39 to someone. This, right, is a bit risky. This gives us another thing we would want from our mechanism, right? The transaction fee mechanism. We want it to be robust to this kind of stuff. Miner incentive compatible, MIC. Well, what about just deciding on a price, a fixed price, posting it to the world, and any transaction with a lower fee would not get in, not pay anything. Any transaction with a higher fee would get in, pay exactly that fee. This is trivially both user and miner incentive compatible. Right? Let's say our posted price, our fixed price is 45. This transaction would pay 45. Right? Trivial. The problem here is that users and the miner can collude. The miner can come up to the green user and say, you want to get into the block, I want to make money. We can both be better off if you sign off that, right? 5, right? 45. I'll reimburse you after. Let's sign a contract which ensures that I won't be able to rip you off. Okay? We're definitely better off. The user will be reimbursed, not pay more, would be included, makes the user happy. The miner makes more money, makes the miner happy. Everyone are better off. This gives us another property we would want, which is robustness to collusion. This brings us to the state of the art. Ethereum's EAP 1559, the mechanism they use currently. It has a posted price, just like we saw. But it burns it, it takes it out of circulation. And the reason is that if no one gets this money, then we cannot reimburse people, right? The miner will not be able to reimburse 5 unless the miner is willing to take it out of its own pocket, right? This takes care of collusion. if the amount of transactions that pay more than this posted price is lower than the block size, then we just take them all. They pay exactly the posted price, which is burnt. And that's it. If the amount of transactions is larger than the block size, then to allow users to compete for this block space, users can attach a tip, extra money, which they pay only when the amount of transactions is larger than the block size. This money is given to the miner in full. This is the only way to incentivize the miner to pick the highest paying transaction. Again, this is resistant to collusion, but it introduces two problems. First is when the demand is high, we revert to a first price auction on the tip, right? And second, when the amount of transactions is low, then miners get paid nothing. Paid less. Because you can think of burning as if we're assigning more value to the remaining tokens, but it's negligible. This gives us another goal, which is to pay miners for including transactions, pay them well. A very natural question, which was asked by Tim Rockgordon, is can we design mechanisms which satisfy all the properties? Reasonable. In a very nice work, Elaine Chi and Ham Chung show that user incentive compatibility and collusion resistance results necessarily in no revenue, which is not ideal. Similar results have been shown in similar settings. Kind of seems like maybe this is a dead end. So in the line of work I'm going to briefly talk about, I showed together with Yutam Gafni, a really good and smart friend, that the collusion resistance notion used in the zero revenue impossibility works is implicitly stricter than the OG, the original collusion resistance notion. Okay? Implicitly, because papers have said that if you set the parameter of the new collusion resistance notion correctly, you get the same thing. We showed no, that's not the case. They differ. Okay. This is nice because given this understanding, perhaps we can get around the possibilities if we use the original notion. To do that, to figure out if indeed we can go around that, we characterize all collusion resistant TFMs, transaction fee mechanisms, auction formats. So I've shown this here so that you would read. No, I'm not. I'm kidding. Like, don't read this. I put this here to scare you, to intimidate you. Okay, like putting the two collusion resistance notions on equal footing and making them comparable is hard. This is why very, very, very smart people have not noticed that they differ. Okay. To give you some intuition as to how they differ, the impossibility notion is kind of a colluding coalition of users and the miner attacking other users. They try to increase their own joint utility at the expense of others, maybe. The original notion used before can be thought of a collusion of the users and the miner trying to attack the mechanism. The mechanisms prescribes some behavior which is not ideal, doesn't give us the maximum welfare. And so the attack, the reasons why people collude is that they can think of ways to improve upon the mechanism and attack on the mechanism. Okay. Given this understanding that the two differ, we characterize collusion-resistant fee mechanisms. We show that they should roughly follow this format. Given a choice of transactions, they should choose the ones paying the most. And if they burn money, like Ethereum's mechanism, then the function which prescribes how much money should be spent is weakly increasing in the number of transactions that are included in the block. And both parts are important. It should be weakly increasing because otherwise you may have manipulations to lower the amount which is burnt. Less money burnt, more money to people. Right? We don't want that. I mean, we don't want that if we want to be robust to attacks. And the function should only care about the included transaction amount and not other things like the fees. Because if we would use the fees, then perhaps the miner and users would be able to pollute to reduce the burn again, right? So if we want to be collusion resistant, we have to rule that out. We then tack on an additional property. First, user incentive compatibility, then miner incentive compatibility. We show that roughly, all collusion resistant user incentive compatible mechanisms kind of look like a second price auction. If it burns anything, then we say how the burn function should look like. And the mechanisms which are collusion resistant and miner incentive compatible roughly look like a first price auction like we saw in Bitcoin. When taking the intersection of these classes of mechanisms, we get that the only, I like that you're nodding, I feel like I'm connecting to people. Okay. When looking at the intersection, what do we get? The trivial mechanism, right? A mechanism which never allocates anything, because the payment functions of this class and that class cannot coexist. We cannot apply them both at the same time. So if you like that line of work, I hope you do. I have more. I show that this framework can be applied to other settings like computation markets. That was a collaboration with industry partners. And I also take a practical approach. I present attacks on real world mechanisms. I implement them in code. I also try to solve things. Again, if you find this interesting, read the papers, come talk to me. Ideally, do both. And this brings us to the future. So this talk shows that the traditional world, the solutions for traditional settings cannot be always directly applied to blockchains and other similar settings. Some additional examples of that. Many systems use authenticated data structures, right? Merkle trees. You can find them in databases, file systems, security standards, all over the place. They're also used in blockchains, but they're not ideal. I show that in one of my papers. And in the words of Peter, it's a DOS risk. We should change this. Okay. Traditional solutions, not ideal for the modern world, or at least the world I live in. This is more on the systems or computer science or whatever side. On the econ side, inequality measures, right, like the Gini coefficient, are used all over the place. You can open up government regulations. People sometimes are very explicit. They write the inequality is this. We want it to be that. So this is why this regulation exists. Right? The Gini coefficient is a very, very prominent, to say the least, inequality measure, used all over the place, studied by a very long and impressive line of work in econometrica, for example. When you try to apply traditional inequality measures to blockchains, you get, let's call them crazy results. Muriel Rubini, a smart person, knows as econ, took a look at Bitcoin's Gini coefficient and was shocked. Seems more unequal, worse than North Korea. But what does inequality mean in pseudonymous settings? Anyone can create multiple accounts, shuffle money around. We cannot directly apply traditional inequality measures to this new setting. So beyond blockchains, right? Anywhere where anyone can create solutions. Another more econ flavor of challenges is the reward schemes used by many platforms in practice, like newcomer bonuses, right? Netflix, every once in a while, at least back in the time, would say, join us and get 1 week for free. Right? If you try doing that in a pseudonymous setting, well, thank you for nodding. People who just join again and again and again, perhaps even people in this room, right? You don't want that. So besides being used all over the place, it's also been studied in academia. Again, disastrous results if you try applying that solution in the blockchain world. And I'm talking to you about these challenges because I've laid the foundations for studying these challenges in some papers. One I recently presented in Singapore, AAAI, and also I sketched the way forward in a couple of grants. I also have even more directions besides these. So again, talk to me after if you are trying to think about the future. So to conclude, Juvenal, an old Roman poet, once asked, who guards the guardians? Right? In blockchains, our guardians are miners. And the guardian of the guardians is the mechanism, right? Which is beautiful, right? Because that's a lot of work for the people in this room, for us, right? Juvenal had in mind the king surrounded by guards. The guards may assassinate the king for whatever reason to get some bounty or whatever. In our world, right, miners are both the king and the guardians, right? The mechanism makes sure they don't do bad stuff. Lots of things in this realm that demand, scream for answers. This requires a huge toolbox, which is very nicely represented by the people here. That's it.